Hello and welcome to the Plastek Academy webinar series. My name is Daniel Prishak and I am the Vice President of Manufacturing at the Plastek Group. Thank you for joining us today. Every individual and every business go about their day doing a certain task or fulfilling a specific responsibility. Perhaps it has become a routine, but chances are at some point in time finding ourselves in a phase of trial and error, adjusting to unexpected variables and finding a means to a best practice. In a manufacturing case, for example, Plastek addresses this concept by embracing the theory of scientific molding. RJG helped us implement this as a part of our process, which in turn established the Plastek brand, providing great quality to the products we produce for the customers we serve. We wanted to give our technical staff the training they needed to be successful at what they do. We were confident that RJG could provide that level of training. We have offered RJG classes to our molding technicians, engineers, maintenance team, and management. The successes we've seen with RJG in terms of machine improvement, employee engagement, and cost savings has led us to use these classes as the foundation of our technical training program here at Plastek. The RJG team has been excellent to work with and have become key partners in our success as we develop and expand our training program. Today I leave you in great hands for this presentation on scientific molding. It is my pleasure to connect you with the team at RJG, our friend Paul Mandeville, trainer and consultant. To everyone watching, thank you for your support and participation. I hope you enjoyed today's discussion.
Great, welcome everybody. Thanks for joining us today. We're going to be going through the reducing material variation through the use of scientific molding, but we're really going to be focusing on the effects on your part, how and why it affects our part. So let's go ahead and get started. There we go. All right, so the injection molding puzzle, all these things are real critical to our process, and they all have to come together in order for us to build this good, robust process. RJG teaches classes in every one of these puzzle pieces, but today our main focus is going to be on the material, looking at that and how it affects our process. So real quick, just a little bit about how plastic is made. When we take all these monomers, we have to combine them together to make these long polymer chains to make plastic. This process is called polymerization. The problem with this polymerization is when we're making these long chains, some of these chains form and start to form sooner, and so they become longer, and some form later, so we have these shorter chains. So because of this, we have all these different chains that we have to deal with, lengths of chains that we have to deal with from day to day, and especially lot to lot. But there's always this variation happening inside of our process. But especially when we change from lot to lot, when they make a new lot of material here, you might have an average shorter chain or average longer chain. But either way, we have to deal with this chain length variation. So a little bit about the polymer chains here. So the shorter chains and the longer chains are going to act differently. They're going to flow differently. So the shorter chains have fewer monomer units or less weight per chain, the number of monomers along there. On the example down on the left side there, that picture, just somebody cracking some candle wax there. It's a very short molecular chain, and so it makes a very weak part. And we can see that in processing too, and we can even cause degradation, which causes shorter chains and will cause parts to break easier. But all chains are going to have some different properties here. So the shorter chains, because they're shorter, they're also going to require less pressure to flow. They're going to flow easier. It's going to take less pressure on the molding machine. The longer chains, obviously the opposite is true, where they have more weight per chain because they're a longer chain. They're also going to be stronger. So in the example there, they have some PEX tubing where they can bend it very easily. It's very flexible and it can bend multiple times. So it has different properties, but it also requires much more pressure from the machine in order to get it to flow. So, this is going to vary from material to material, but also keep in mind, this is going to happen within your lot of material, especially from lot to lot. So this is ongoing change we have to deal with. So that's what brings us to the viscosity. So the definition of viscosity is basically a fluid's resistance to flow. So how thick or how hard it is to flow. So in the example on the left here, it looks like maybe some water or something here. Has a very low viscosity because it has a very low resistance to flow. We're on the right side, we have a higher viscosity material, meaning it's a lot harder to flow, a lot thicker material. So on the left, you got water or alcohol maybe. On the right, think of like a syrup or honey. It's got a very high viscosity or very high resistance. So when we're dealing with these different lengths of chains, so we have got a batch A here with a short chain on the bottom, and on batch B here, it's a much longer chain. So ultimately, it's going to affect our process. It's going to affect how easily it wants to flow or how hard it is to flow. So it's also going to have an effect on our part properties. So we've got a general Bell distribution curve here. If we're looking at size, well, one's going to flow easier, so you might get more pressure in there, but it's going to have different properties. So we have to deal with this ongoing change throughout our process. So one of the ways we can look at it up front or early on, when we get our materials in, if you look at the certs, a lot of times you'll see something called MFI or MFR, melt flow index or melt flow rate. There's also melt flow volume out there as well now. But basically all this test is doing is they're putting some material into this heated barrel here. They put a given weight on it and we let it leak out. We give it 10 minutes a time and we just weigh how much material leaks out here. So in this example, the MFI number is 10 because we had 10 grams of material that leaked out of there over that 10 minutes. So over here on the right, here's another example of another material. Maybe this was a virgin material versus regrind material. Maybe it was two different lots. But you can see when they did the same test for the same amount of time and the same weight, now 16 grams of material leaked out. So the MFI number for this one would be 16. So you can see already one's going to have more resistance to flow, the 10, because less came out, versus the 16. So it gives us a representation of how our material might be coming in the door and how, well, of how it's coming in the door, but also how it's going to flow through our machine. So viscosity, that's probably the biggest challenge we always deal with on a day-to-day basis. But there's other ways that viscosity can be affected. Like I mentioned, regrind. If we're running regrind, the moisture content. If you run wet nylon, it's going to come out very, very thin or flow very easily. If you ever had any experience with that, your heater bands. Versus the actual melt temp, just because you set your heater bands at one temperature doesn't mean that's the temperature that the material is actually going to be based on the machine's dynamics, the resonance time, the screw design, and all that. Back pressure variation, or if you're changing it at all, that's going to have obviously a big correlation to our melt temperature as well, because we're going to be working it harder, shearing it more. Same with screw recovery. We don't want to be, well, that's going to have a direct effect, correlation to viscosity. Additive content, what kind of additives you putting in there could make it thicker, or maybe make it much thinner, especially like maybe a colorant. Cycle time, again, we're talking about resonance time, how long that's sitting in there. It's going to have effect on how heated that material is, or maybe it sat in there so long it got degraded. Injection speed, consistency of the machine. The faster we flow material, the easier it's going to be to flow. And so we want to make sure our molding machine is very consistent and capable. And there's other things too that can have an effect on our viscosity. So we have to keep all that in mind. But even if you control all this, we still can't, resolve the fact of the material is going to have this different viscosity every day, from day to day, shift to shift, lot to lot. So we get thicker and thinner material. So, we think, well, maybe, no big deal. We can adjust for that with the machine. But in reality, so when we inject our material, we do it under velocity control for a proper decoupled process. And the reason we go under velocity control is it's like setting cruise control on your car. You set it at 55 miles an hour. It doesn't matter if you hit a hill, go up a hill, go down a hill, your car should maintain 55 miles an hour. And so that's what we're trying to do with our molding machine. During fill, we set it to a speed control or velocity control. So that way we got our cruise control on, we can just ignore what's happening to the thicker or thinner material. And I say ignore, but we're only minimizing it. It still will have some effect, but at least we're not under pressure control. However, after we fill our part 95, 98% full, the screw stops here and it transfers to a pressure control, pack and hold pressure. And so when the machine is under pressure control, the thickness or the thinness of the material is going to have a direct correlation to our part quality. We're no longer under speed control, we're under pressure control. And so now if it's a thicker material, you can see the material in front of the screw here. It has to, we got that material, it has to come out of the nozzle, has to go through the screw, the runners, the gates, the parts. And the parts are usually very thin, high pressure loss. But I don't care if there's a hot runner or a cold runner, you're still going to have some pressure loss throughout the system. So when we transfer into pack and hold pressure, and this is a thicker material, it works as an amplifier. So we got a higher viscosity material down here, or a thicker material. And so we transfer to pressure control. And now all this material is going to be thicker. It's going to be more viscous. It's going to be harder to push, harder to transfer energy. And so the longer that system is, the more, the harder it's going to be to transfer that energy down. And so, excuse me. So to an extreme example here, we can get short shots throughout this whole amplification process. So over here on the left side, static pressure gradient or pressure loss is a major cause of part variation. It can only be measured using mold pressure sensors. So we only know what's really happening down in the cavity if we have sensors in there. As we transfer to pressure control, the machine is just going to push a specific pack and hold pressure that you set. And so number 2 here, it varies directly with effective viscosity. So once we transfer to pressure control, it's a thicker or thinner material. It's going to directly correlate with how thick or thin to our part quality. And then lastly, their pressure loss is always large in plastics. Plastic is a very thick, viscous material, and there's always going to be just a ton of pressure loss in there that we just have to deal with. So the opposite is true here, the lower viscosity. I'll explain this again a little bit here. So the lower viscosity means less resistance to flow, a thinner material. Well, the thinner this is, the easier it's going to be to push, but also the easier it's going to transfer that energy. And so once we're under the pressure control, if it transfers the energy too much, basically we can have flash. So we can get flash at the top here, this curve. Okay, so example, decouple molding 2. I love seeing this curve. I've worked with many E-dirts, and even before I started teaching these classes, I'd see these curves all the time, and I knew it was happening. I just didn't realize how nice the curve was, I'll say. So what we're looking at here is the red line is, well, this is an E-dart screen. The red line represents the machine pressure, how much machine pressure it takes. And this is over a time. Let's see, we got 0 seconds down here on the left, and we got 11 seconds over here on the right. So this is over 11 seconds. It looks like to maybe be about 50 cycles overlaid. So this is 50 shots on top of each other. So during injection, you can see that there's variation in pressure. And that's actually what we want to see, because the machine's under velocity control. So it's using whatever pressure it needs to. That's one of the keys to decouple molding. We want to give it an abundant amount of pressure during fill. So, maybe we still limit that pressure a little bit as a safety factor, but during normal production process, we don't ever want to be pressure limited. We want to control the machine using velocity. And the reason, remember, for that is that we can minimize the changes of viscosity on our process. So during injection here, this is a first stage, then it transfers down to pack and hold pressure. Comes down, and then eventually it will go up to back pressure and all that. This green curve here you can see is a gate sensor. So this is actually the pressure inside the cavity. So during injection, this pressure is varying, and that's telling me, well, the viscosity is varying. We're minimizing the effect on the process because we're under velocity control. However, eventually I transfer the machine over to pack and hold here, and now you can see what happens to that red line, the pressure variation. It just smooths right out. For example, maybe we set our hold pressure or pack and hold pressure to 500 if it's hydraulic, maybe 5,000 if it's a specific pressure electric machine. But once we transfer to pressure control, the machine is very stable now. I mean, now we're not controlling by velocity, we're controlling by pressure. So we told it to go to the set 5,000 specific pressure, and it hit it. It hits it dead on and stays consistent. So during fill, we've got a lot of variation. Then we go to pack and hold, and now it's very consistent. But now look what happens down here in the cavity sensor near the gate there. At first, it was very consistent because we're under velocity control here. But then once we transfer to pack and hold, well, that variation disappeared on the machine. It's stable on the machine, so it had to show up somewhere. So during fill, we're ignoring changes in viscosity, well, minimizing. And then we transfer to a controlled pressure, and that variation has to show up somewhere. Remember, the material, if it gets thicker or thinner, it gets harder to transfer that energy, and you're going to see the effects on your part quality there. So a couple questions over here on the right, just something to think about. What effect could a 10% viscosity change have inside the mold? So so let's look at this. During fill, let's say this highest curve here, this highest point here, it took a lot of pressure to fill that in. So it tells me it was a very thick and viscous material. And that's fine. From shot to shot, we get this normal variation. So it was a really thick material to transfer, or to push in there. Once it transfers to pack and hold, well, now it's thicker. It's going to have less pressure. So that top line here on the red is probably going to be the bottom line here on the green. Once we go to that pressure control, and that's much thicker material, it's going to be harder to transfer that energy in there. And so at a certain point here, so what effect could a 10% viscosity shift have? Well, maybe this is not enough pressure. Depending where the sensors are and all that, maybe it's even a short shot. And then opposite up here is true. Maybe these are flashed out parts. So we could actually set limits on these if we have an EDART and we're controlling that, we're monitoring that. So next question here, if a viscosity change happens that requires recentering of the process, how can the parts be contained? So, how are you doing it today on the floor? Something to think about. If you're utilizing an EDART, you can monitor effective viscosity as well. But at the very least, even if you're not running with EDARTs, we should be watching some machine alarms. We should be triggering some alarms on maybe pressure or cushion or whatever important to your process. And then if you make a bad one, what happens? Does the machine go in alarm? Does the machine stop? Does the machine just keep running and the parts go into your good bin? So at RJG, we can put in this EDART. We can help you understand these alarms and how to control it. You can set up so even if you're not running an EDART, you have these alarms on your molding machine, you can set up your conveyor belt to run full-time reversing conveyor, which just means it's a fail-safe in case a connection or something goes bad. Basically, the belt will always run backwards all the time until the machine or the EDART says, oh, I got a good part. And every time it has a good part, then it runs the belt forward. That way, if the wire gets crushed or something happens, it won't just keep running good parts in the bin when they may be suspect. So just something to think about, as you're running along, what's happening to those parts when your machine goes into alarm. Maybe you're making short shots, maybe you're making flash, but the one thing I can guarantee you is you have viscosity changes happening right now on your floor, and how are you handling it? So there's some best practices there to do that. Okay, so decoupled II, or commonly known as scientific molding as well. All right, so the objective here is to fill the mold fast, transfer by screw position, the cavities are 95-98% full. At that point, the melt inertia is used up just before the cavities fill out, and second stage hold pressure is used to complete the filling and pack out the parts. So we fill the mold quickly, we transfer by screw position. So we set that on our molding machine when the parts are 95-98% full. So the melt inertia, I just want to reiterate this a little bit. The melt inertia is used up just before the cavities fill out. So that means the screw's traveling very quickly. The screw needs to stop. That material in front of it's all compressed and being pushed by the screw. So that inertia needs to all slow down, work its way out, and then we transfer to a very controlled hold pressure. So a little demonstration here at the bottom. You can see the molding machine nozzle right here. I'm going to click on this animation. You'll see the plastic fill in here, and we got two sensors here, one post gate and one end of cavity. So during injection, we're going to fill out that cavity 95-98% full. We don't quite want to fill it out. because we're going really fast and we don't want to slam that plastic into the end of the cavity. It will actually overpressurize it and blow your mold apart and cause a little bit of flash. So we fill it very, very quickly up to 95, 98, transfer to pack and hold. And you can see the machine drops down to pressure control here. The cavity pressure of the post gate continues to rise a little bit until we're 100% full here, well, up here. So once the sensor gets pressure, then the holding time begins and shrinking starts to occur while we're waiting for gate seal, and then we'll go on with the next cycle here. So that's the essence behind decouple molding. We have to fill it, well, we want to fill it quickly, and we'll talk a little bit more about that. But we have to give it an abundant amount of pressure, so it has velocity control. All right. So here's an example of filling the cavities. One's faster than the other one here. So this top example here, packing after fast fill of 0.35 seconds, and this bottom one's at 0.7 seconds. So it's double that. So in both examples, so we got this long part here, and we got a sensor on each end of it. And so that's kind of what this is down here. It's blown up of this, the first part near the gate. So you can see we have a sensor pressure of 4,400 PSI specific pressure. And same way down here on this lower example. Because, well, so now up here on the top, on the end, if we had a sensor way down here at the very end of the cavity, we have a cavity pressure of 2,900. Okay, so now let's look at the bottom example here where the fill time is twice as slow. I should 0.35 to 0.7. So we got that same 4,400 at the gate, but now at the end of the cavity, we only have 1,700. Because the slower we push plastic, the less molecular alignment the long molecules will get, and the harder it becomes to push. And so the slower we push it, it's not going to transfer as much energy down to the end of the cavity. So that's just one of the advantages. The faster we fill, the more pressure we can get to the other end of the part. And that can help with, it could potentially help with warp. It could, you could actually, in effect, the faster the fill time, if I can get 2,900 down here at this fill time, if I need 2,900 down here, I'm gonna have to push with a lot more pressure. So it's possible that the faster you fill, it's going to push easier, it's going to get more of that pressure down there. And it's possible that we can even reduce part weight because we don't need to pack out the gate end so much. So I've talked about a couple reasons here. The faster the fill speed, the better. In a lot of ways, yes. Some materials can't go too fast. We know that. Some materials will just shear out. And there's machine limitations too. So let's look at these bullet points here. A single fill speed should be used whenever possible. So yeah, the faster we go, the better for our process, so we can get more pressure down there. Now, if you have to profile, the only reason we're going to profile it is to slow it down. And if we have to, we have to. But if possible, just use one. So this is the fastest way to fill, because if we profile, we're only going to be slowing down. We're not going to be slow and speed up, generally. So this is a simple setup. Let's keep it simple. Just put it in one speed and then let it go. And then lastly, profile fill speeds may be required if flow-related defects occur, such as gate blush, burns, etc. So, I mean, it's common with like lens molding that they fill in a cold run, for example. We'd fill very quickly to get through the sprue and runner, but then during that gate, we'd have to slow it down so we didn't cause any gate blush. And then at the end of throughout the cavity, we want to speed it back up so we don't stall our flow run out. So it's very common to see 3 speeds with like lenses, but if you don't need it, don't add it. Just another variable. We don't want to slow it down if we don't have to. So choosing the best fill speed. We always want to fill as fast as the machine will allow without creating flow-related defects or inconsistencies. So at the bottom there's a couple, so this fill fast as machines will allow. Some machines will be the least capable target on which a mold will run. We can't just run it as fast as it will go in the fastest machine because, well, let's face it, scheduling or planning might have other ideas to put in other machines as well. And so we've got to look at all the machines, not just the one. So the least capable target machine on which mold will run for speed limit, pressure limit, and clamp. We have to look at all those things when we're trying to target a machine for a mold. Without creating flow-related defects, number 2 down here, fill defects include blush, strength, optical, paint adhesion, jetting, burning, air traps. So there's a lot of different reasons that we might, a lot of different defects that we might have to change this fill speed on. And then it says, without creating flow-related defects or inconsistencies. So number 3 down here, inconsistencies include cavity imbalance, material changes, shot-to-shot variation. So, we got to make sure our machine's capable of it. So choosing a fill speed. So this is a study we go over in our classes, the fill flow study. So we're not going to get into great detail of how to do this right now, but we'll talk about it a little bit here. So basically, we're just doing 10 different speeds from the machine's maximum to the machine's minimum. We're recording the transfer pressure, the fill time, and it can calculate out the volumetric flow rate. And then over here on the right, we're just going to record any defects we see or machine problems. Maybe we had some burning when we went too fast up here. When we went too slow, the flow front was stalling. So obviously we can't go any slower than that. And then any other defects you might be seeing or having problems with your parts, you would record in here. So what we're looking for is a minimum acceptable flow rate range down here on the left, and then a maximum acceptable, and then what you picked. So we want to go faster the better, but it has to be capable in all machines. So up here we have the machines. We have 3 different machines listed. There's screw diameters. You put that in. This is a calculated cell here. Anything in orange is calculated. So this gives you your screw area, the maximum linear speed of the molding machine, and with that information, it can figure out the maximum volumetric flow rate, because we're trying to normalize the data, trying to make sure all machines can push that same volumetric rate, as that might change as the screw diameters change. And then the maximum system pressure of the 3 machines. So we go from that, and we get a little graph here on the bottom. X-axis, we got the flow rate of all molding machines, and on the Y-axis here on the left, we got the specific pressure of all the molding machines. So this graphs it out for you, where we pick a fill speed. So along the bottom, we could list out all the different defects we had, and they had defects like pretty much up to 8 and started up again about 9.5 or something. But the point is, we're picking our fill speed of what it can run in all 3 machines and make a good part. So up here we have the 3 machines or maximum pressures. So machine 3 here has a maximum pressure way up here. We're never going to hit that, no matter what fill speed we picked. Machine 1, we're never going to hit that pressure. Machine 2, well, this is the fill speed we picked, and you can see we're pretty close. We're not quite there, but we're pretty close. So that's fine for today, maybe, but maybe tomorrow the viscosity is going to shift a little bit, and the machine's going to need a little bit more pressure, so that one could be an issue. And then it also, we consider in the maximum flow rate of the 3 machines, these vertical curve lines over here. So you can see it's capable of running on all 3 machines. For flow rate, but pressure might be limited on machine number 2 here as the viscosity change happens. So it's just another way of, of course, we want to go faster the better, as long as you're making good parts, of course, and it can run in your targeted machines. So that's just the way that we're comparing all the machines, trying to normalize the data and making sure it can run in what's selected. Okay, so the effective viscosity variations. This is just some hypothetical numbers here. So if we had 10,000 PSI in the molding machine, and we had a mold cavity pressure, a mold pressure of 3,000, that means we had 7,000 pressure loss. So if you remember, as the plastic gets thicker or thinner, it's going to transfer that energy easier or harder. But the cavity pressure, you can see, so we started up here with this mean of 10,000 and 3,000 here, and then we had the viscosity increase by 10%. So quickly you might just think, well, the cavity pressure is going to go down maybe by 10% once we transfer that pack and hold, and it's harder to push. But in reality, this cavity pressure dropped by 23%. So that's because the 7,000 pressure loss that we had up here, that will directly correlate to the viscosity change. So 10% of 7,000 is 700. So if we add that into this here, as the viscosity went up by 10%, the pressure loss also goes up by 10%. And so the mold pressure is only what's left over. So if we take 10,000 minus 7,700, that's where we get our 2,300. So a shift in viscosity can have huge effects on our cavity pressure and our part quality. In this case, it was a 23% decrease. Then opposite is true. If the viscosity decreases by 10%, the pressure loss will also decrease by 10%. Remember, that was the 700 that we added up here. Now we're going to subtract it, and our mold pressure goes up to 3,700. So remember that mold works as an amplifier of the viscosity changes, of the viscosity shifts, and we just have to do our best to process with that. So these effects can be even exaggerated even more if you had a bigger mold or more pressure loss, maybe thinner walls, a longer flow section. So that's what this example is here. We had a mean of 18,000 this time on the molding machine, and still the same cavity pressure of 3,000. So we had a total of 15,000 pressure loss. So now we have the 10% increase. Well, remember that pressure loss is what's going to vary directly to the effects of viscosity. So viscosity goes up by 10%, so does the pressure loss. So went from 15,000 to 16,500 now. So what's left for the mold pressure? Well, it's the 18,000 minus the 16,500, and now we only have 1,500 left in the mold pressure. So that's actually a 50% decrease. So again, these are just hypothetical numbers, but if you think about the mold pressure, how that's going to directly affect, the more mold pressure we have, the more the amplifying effect is, and the more it will have an effect on our part quality. And we just don't know what's going on inside the cavity unless we have sensors to actually see it. And so that's a high pressure process, so we have to think about that sometimes with high pressure processes. Are we in a good, capable machine, robust machine? So some effects of pressure variations in our cavity. So we know this pressure variation is happening. When we get a short shot, for example, well, that's going to be a low pressure condition in the cavity. We didn't have enough plastic. Flash would be a high pressure condition in the cavity. Sinks, kind of the same thing. We just didn't have enough pressure to pack out the part and compensate for shrinkage, and so it was a low pressure condition in the cavity. Dimensional variations, well, that could be anything. It could be too much or too little, so that could be any pressure deviation. The defect of warp, warp is caused from differential shrinking. And if, let's say we're pushing, if you remember back a few slides ago, that example, when we're pushing fast versus when we're pushing slow, it was a lot harder to get that pressure down to the end of the cavity. And so warp, it can be caused from too much pressure at the gate end and too little pressure at the post, at the end of cavity. And so differential and shrinkage. So warp can be caused from a difference in pressure or pressure gradient. Gloss gradient. Well, if we don't have enough pressure, low pressure condition in the cavity. So if we don't have enough pressure, maybe we're not packing it out properly and we're not imprinting that cavity surface of the texture. And then strength here, it could be any pressure deviation from the part approved process. Maybe we have too much pressure, maybe we don't have enough pressure now. All right, so what's next? Pick the right molding strategy for you. So RJG, well, we have traditional molding back here. This is what we did a long time ago before we put science to this process, early days of molding. So it was all pressure limited. So the problem with that was it was always directly at the mercy of how thick or thin the material was. So now we put some science to it, and we've talked a lot about decoupled molding 2 today. So we give the machine an abundant amount of pressure to fill out the cavity 95–98% full, and then we switch to pack and hold. So that helps us eliminate a lot of variation because we can ignore or at least minimize the effects of viscosity for the first 95–98% full of part. Decouple molding 3 down here on the bottom right. So that's where we're going to actually start to implement sensors in the tool. We're going to put sensors in there, and we're going to fill out the cavity, and we're also going to pack the cavity out all with velocity control. So the more we're under velocity control, the more we can ignore the effects of how thin or thick that material is. Now we'll still have an effect, but we can even minimize it a little bit further. So decouple molding 2, we talked about today, we're ignoring, we're minimizing for sure the effect of viscosity during 95–98% full of part. That's pretty good. But we still have to switch to pack and hold. And so that's where we're going to get variation. Decoupled 3 is going to reduce even more of that variation because now we're going to fill the cavity and pack it out until we hit the right amount of cavity pressure. Then the sensor tells the EDART tells the machine, okay, we got enough pressure, now switch over to pack and hold. So it's just a way that we can reduce a little more variation. Decouple molding 1, you might have heard about that in the field as well. It's not like the first, you know, we didn't build these in order or anything. This wasn't the first way we determined how to do molding or anything. Just the names we call them. So decouple molding 1 is actually very similar to decouple molding 3, but it's made for more thin wall cavity stuff, super thin wall stuff. So hopefully we're not doing traditional molding today. Hopefully we're at least doing scientific or decouple molding 2. And then if you had some part quality issues or customer complaints, maybe it's time to look at decouple 3. You know, if you're making a dog dish, you probably don't need that level of control, but if you're making an implantable device that goes in the human body, you know, that's something serious to consider. So here you can see the traditional molding that I just talked about when we were all pressure limited. When we had viscosity changes happening in our mold, so this is a 20% viscosity shift that we put in all 3 of these processes. And you can see the blue and green lines here are cavity pressure sensors, and you can see how much variation we had in those 50 shots. We're decouple molding 2 that we want everybody to at least get to today, because you don't need an EDART. I mean, you can use an EDART for monitoring, but you don't have to have an EDART to control your molding machine. It's just using the molding machine the way it is right now. And you can get a lot of that variation out. You can see the cavity pressure here, and the range of those 50 shots are much, much tighter. And then decouple molding 3 over here, you know, with the sensor control, we can even reduce that even further to get the best part quality even yet. So training your staff, you know, the benefits of training, you get higher productivity, you get actually less turnover, less waste, higher employee morale, less micromanaging, and many more. So RJG has a whole gamut of classes, depending on the level that you're at, where you need to start at, maybe the direction you're going. So our RJG offers award-winning online implant classes and classroom-style training courses around the globe for all experience levels, led by industry experts. So we have many facilities in some different countries. We have currently 3 here in the US, but we also travel to plants and we train these classes as well. You know, with the pandemic and all that, we do a lot of classes online as well, but we still do implant classes as well. Okay, so when you're going through the courses, if you're focusing more on the process side of things, this is a kind of a basic scientific process, how we build it, and this is what we teach it from. So all these lab sheets are available in hard copy as well, but we also have this all in Excel, so we can go through it very quickly. And we verify the machine, validate the machine. Here's our machine benchmarking test. Over on the right, our process development test, how we build the process. And so we actually step through this step by step, how to build a scientific process, how to make sure your machine is good, and you know, try to address it from the scientific point of view so we can minimize variation as we go. And that's our website. You can always contact us if you have any questions or if you want any additional training. Other than that, I will hand it back over to you, Nicole.
Hi there, everyone. Thanks for joining us today, and thank you, Paul. As Paul mentioned, my name is Nicole. I am the marketing manager for the Plastek group, and we're going to move to our last section of today's webinar, the famous Q&A session. So while we keep ourselves on schedule today, we do have a few moments. I see a great group of everyone online with us today. So please take this moment to jot down some questions in the chat box there and send them over to myself and Paul. Like I mentioned, we'll get as many answered as we can for you today. While we wait for your questions to come in, I am also going to just comment on top of the many great things that have already been shared with you today from Daniel Prishak in our intro video and Paul here, our partner at RJG. Thanks again for being here with us and providing your expert knowledge. We've had the benefit of seeing Paul here on site, as he mentioned, doing some training here in addition to the virtual classes. So I heard Paul mention a couple times, you know, we're just going to go over this briefly today, and there's more in-depth sessions. So One thing I want to remind you before you leave the webinar today is our handout sessions. RJG has provided a brochure packet in the handout link on your dashboard. Before you exit the webinar, go ahead and open those PDFs so that you can access them after the webinar at your convenience. We also have our contact information up here on the screen so that you can feel free to reach out to either of us on today's topic, more training through RJG, or even within the Plastek Academy. So you can jot that information down as well. Okay. Do you see your questions coming in? So Paul, we've got a couple. If you're ready to come back on with us, we will get started with those questions.
All right.
Okay.
Sorry, it took me a second there to come back.
Yeah. All right. So we have some questions about training, about your content today, and also locations and accessibility to your resources. So in terms of location, do you have an RJG branch in India? And then we also have, if you're working from Portugal, where would training take place?
Yeah, those are great questions. Let's see another one. I don't know all the locations, unfortunately, off the top of my head, as I haven't traveled to many of them, especially recently. So I'm not sure exactly where the locations are globally there. I know we have one in, I believe, in Germany, in China, UK, but we do teach in 9 different languages as well. So I would just recommend calling or contacting RJG and determining the best location for your plant to get training at. Or, we can also do it online as well.
Okay, great. Okay, so in regards to the presentation and some content here, when you say fill fast, should we keep in mind fast might be actually slow based on the application and the mold?
Okay, good question. So yeah, there's just benefits to filling fast. So the faster we fill, there are certain benefits that we can reap, but we certainly can't always go as fast as possible. We have to take those things into consideration of your machine's capabilities and the materials capabilities. So there's benefits to filling fast, but you can't always do it, and that's what it is.
Okay. All right. We have another question. Looks like, speaking from experience during a production process, someone came across constant pressure process where the screw velocity varies to maintain pressure constant.
Yeah, absolutely. So there are some processes out there. There are some other companies that are working with that, and there are sometimes benefits to doing that. But for the most part, it's a pressure limited process. So as when there are some benefits to it, it's not a solution that's going to answer all your problems. It's for a niche type of jobs.
Okay. And then let's see. Looks like a comment. If you could discuss pressure sensors in the machine nozzle versus the cavities.
Okay. Typically, we don't put sensors in the nozzle. I'm not sure I've ever seen that. In fact, maybe as a scientific experiment or something. But the closer, so as that viscosity goes up and down, it's going to be thicker or thinner, and like I mentioned, it's going to transfer the energy easier or harder. So if you have a sensor way back there in the nozzle, once you transfer to pressure control, that's great. You can see the pressure in the nozzle. The machine should give you pretty accurate pressure too, right behind the screw that's pushing it. But as that viscosity changes, it's not really going to tell you what's going down inside the cavity. So the closer we can get in the cavity, the closer we can get to end of fill, the more realistic data we can get, the better resolution data we can get.
Great. Okay. We did cover all of our questions. There is one more that I see here submitted, but I will answer that in my closing statement for today. And before I do so, Paul, would you like to close out with any statements for the group?
Well, just thank you very much for participating today. Look forward to feel free to contact us for any additional information. And I'd just like to thank Plastek for offering this free online webinar.
Wonderful. And we certainly thank you again, Paul, for being here with us today.
Thank you.
And then to answer the last question in our parting today, will this webinar be available and being possible to share the presentation? To answer that, the Plastek Academy can be viewed on demand at your convenience to either revisit and go over the webinar again and take a look at that information, or even share it with your coworkers, students, any other individuals that you think may benefit from it. So that can be found, all of our Plastek Academy series presentations can be found at plastekgroup.com, or further plastekgroup.com/plastek-academy. And again, you can watch any of our series webinars that we've done since September of last year. So that's one way to re-access this at your convenience. Other than that, again, you have our contact information. We will be continuing this series through September of this year with a wrap-up. So stay tuned and check out our other topics to come with our other experts that we partner with here at the Plastek Group. Thank you again, everyone, for joining. As you exit today's webinar, there will be an opportunity to complete a brief survey for us and give us some feedback. Thank you and have a great day.